In sections 2.1 and 2.2, we kind of developed what a derivative was. We worked with limits and then worked our way up to what a derivative was. And so far, we've been using the definition of a derivative to find the derivative of a function. Um, there are shortcuts for that, and basically they all kind of come from more or less us working with, you know, this same kind of general rule that we've been using, of the definition of a derivative. Of course, it gets a little bit more complicated as the functions get a little bit more complex. So, um, but over time, patterns developed, and we have these rules for a derivative. So if I'm taking the derivative of a constant, that's just going to be 0. So if I do the derivative, if f of x equals a number, there's no variable x in there, and I want to do the derivative of that, it's just going to be 0. So that's a pretty simple rule. There's a power rule, and that rule for constants kind of comes from this power rule. Also, as we deal with, the derivative of x itself, it's going to come from this power rule. Essentially, the power rule for a derivative says if I have x raised to a power of n, if I want to find the derivative of that function, I just take the exponent n, multiply that to the x, make that a coefficient, and then I subtract 1 from the exponent. So the derivative of x to the n power is given as n times x to the n minus 1 power. Coming from that power rule, if I take the derivative of just x, I end up with 1. The constant multiple rule basically says if I have a coefficient in front of a power of x or any other kind of function of x, I can pretty much just ignore it and let it go along for the ride. So, the derivative of c times f of x is the same thing as me doing c times f prime of x. And I'm going to kind of show what that looks like as we go through some examples momentarily. And again, if I have a constant times x raised to the first power, the derivative of that's just going to be that coefficient. So for instance here, if I do a derivative of 5x to the third power, well, the 5 just sticks around because it's carrying along a constant coefficient. According to the power rule, the derivative of x to the third power is going to be me moving the 3 in front and getting a new coefficient of 3, and then taking x to the second power because I'm going to subtract 1 from the exponent. Now, of course, when I simplify, I'm now going to multiply that coefficient I let go along for the ride, and I end up with 15x squared. Similarly, if I have 3x to the negative 4 power, I'm taking its derivative. Again, the 3 kind of goes along for the ride. The negative 4 is brought in front of the x, and that's why it ends up here. And then I take that power of x, and I subtract 1 from it. Negative 4 minus 1 is negative 5. So I end up with 3 times negative 4 times x to the negative 5 power, which I can write as negative 12 times x to the negative 5 power. I can also write that as negative 12 over x to the 5th. Excuse me. So in the example that I just asked you to do, I asked you to find the derivative of this function here, 5 times the 4th root of x to the 3rd power. Now to do this problem, we have to kind of go back to some rules of exponents we studied back in chapter 1. And namely that, when I deal with any kind of radical or any root, I like to rewrite that as a power, because then I can use the power rule. And that's one of the reasons why we were talking about using that, is because, although they do have specific rules for roots, it's a lot easier to use the power rule rather than do some of those other obscure rules to do it. So the first thing I do in this case here is, instead of 5 times the 4th root of x cubed, I'm going to change this into 5 times x to the 3/4 power. Same thing. And now I'm going to use both the constant multiple rule and the power rule. So essentially that constant multiple, that coefficient of 5 is going to go along for the ride. And then I'm going to take that original exponent of 3/4, move it in front of the x, and then take the exponent of 3/4 and subtract 1 from it. So I'm going to have 5 times 3/4 times x to the whatever 3/4 minus 1 is, that power. Well, 5 times 3/4 is 15/4. 3x to the 3/4 minus 1 is a negative 1/4, so I end up with 15/4 times x to the negative 1/4 power, which is 15/4 x to the negative 1/4 power, or 15 over 4 times the 4th root of x, which kind of goes along with choice B in this question here. As we continue in these examples to go through some derivative rules to help make our task of finding the derivatives of particular things a little bit more easy than to use the limit definition, we have the sum rule. And basically the sum rule is pretty straightforward and becomes much more useful as we move into more complicated functions when I have things other than powers involved. When I start getting other roots and other functions involved, it becomes a little bit more useful than what I have in some of the instances here. But essentially the sum rule also falls into differences as well. If I take the derivative of the result of two different functions being added together, it's like me taking those two individual functions separately, taking their derivatives, and then adding that result together. As I said, the same thing occurs with the difference. So the sum rule actually also refers to differences as well, because remember, in the scope of algebra, addition and subtraction are essentially the same thing. All subtraction is adding by a negative. So that's why they have the same precedence in the order of operations. There's really, in an algebraic way of putting it, there's not much difference between the two. So the sum and difference rule for derivatives are basically, if I have a function made up of the sum and or differences of two or more functions, and all I have to do is take those individual functions, take their derivatives individually, and then carry through the addition or subtractions as previously defined. So let's have a look at an example where this comes into play. So if you're given here that f of x equals 2x cubed minus 5x squared plus 7. Now, we don't have a rule for this. We have a power rule. We have a constant multiple rule. So if I take these three functions separately, take their derivatives, and then carry through the subtractions and additions as defined in this function, that's going to give me the same thing. So as I go through this example here, when I take the derivative of 2x cubed, I get 6x squared. When I do the derivative of 5x squared, I get 10x. And what you don't see here is that essentially I do have a plus 0 here because the derivative of that 7 is nothing. So f prime of x is just going to be that 6x squared minus 10x. Now, f prime of 2 is just me simply plugging 2 into that new function. So everywhere there's an x, I'm going to replace it with 2. So I get 6 times 2 squared minus 10 times 2, which is 24 minus 20, which is 4. Now it's your turn to try finding the derivative of a function involving the sum and or difference rules, along with the other rules we learned previously. So for this function that you were given as an example to try yourself, we have f of x equaling 8x squared minus 8 times the square root of x. You were asked to find f prime of 4. So the first thing I'm going to do is find f prime of x, which means I'm going to take the derivative. But before I even do that, I'm going to take that 8 square root x and make it 8 times x to the 1/2 power, because we have a power rule. We don't have a clearly defined rule for the square root symbol, although there's one that exists in some calculus books. It is easier in the long run to handle it, using the power rule and then convert back to a root if you need it. So, given that this is the function, when I do f prime of x, I'm going to take the derivative of 8x squared, the derivative of 8x to the 1/2 power, and I'm going to subtract those two derivatives to get the derivative of this function. The derivative of 8x squared is 16x. The derivative of 8x to the 1/2 power is going to be 4 times x to the negative 1/2 power. I multiply the 8 by the 1/2, subtract 1/2 and 1, and get the negative 1/2, so that's how I get that. I can also turn that to a root if I want to, and I do. So f prime of x is 16x minus 4 over the square root of x. Always look to make sure that you see how they want you to define those functions. Sometimes they want you to leave it as x to the negative 1/2 power. But knowing what that means is also important, and knowing it's the same thing as me having square root of x in the denominator is what's going on here. So now when I plug in 4 for the x and do f prime of 4, I'm going to have 16 times 4 minus 4 over the square root of 4. 16 times 4 is 64. 4 over the square root of 4 is 2. So 64 minus 2 is 62. So the answer for this, f prime of 4, is 62. Now, where we use some derivatives, especially in the business calculus course, is dealing with what they call marginals: marginal cost, marginal revenue, marginal profit. And those are basically rates of change for, those particular things. And so suppose that we have these generalized functions. R of x is the total revenue from selling x units. C of x is the total cost of producing x units. P of x is the total profit from producing and selling x units. The marginal cost means, and they kind of phrase it a little bit differently. They say it's the additional cost of producing one more unit at a particular value of x. Essentially, what it is, it's a rate of change. It's still a rate of change. It's essentially, if you produce so many units, at that moment, what's the cost of producing, an additional unit, or what's overall is the cost of producing each of the units overall that you produce? I mean, it's a rate of change. It stands to reason that because there's certain costs that you may have that are fixed and some that are variable, that sometimes the more you produce, sometimes that would have that would mean that the cost per item is smaller. Whereas in some other cases, depending on what those other individual costs are, the more you produce, the more it costs per item. It really depends. I mean, so that's what the marginal cost essentially is. Now they define it as a difference quotient, but it's basically a derivative. So if they ask for a marginal cost, you're basically finding a derivative of the cost function. If you're asked to find a marginal revenue function, you're asked to find the derivative of a revenue function, and same thing with profit. So marginal profit is the derivative of a profit function. And that's what they kind of discuss right here. So marginal basically means derivative of. And it's, again, and we have these interpretations: slopes, instantaneous rates of change, derivatives, and now marginals. It's another word that you have to be kind of aware of, that kind of indicates that you need to take some sort of derivative. So this example here, example 3, finding and interpreting a marginal cost. The Pocket EZCIE is a miniature keychain flashlight based on LCD technology. The cost function is given below there. So 8 times the 4th root of x to the 3rd power plus $300, where x is the number of EZCIEs produced. I don't like the way that's even pronounced. So they want you to find the marginal cost function, and they want you to find the marginal cost when 81 Pocket have been produced, and interpret your answer. When they say interpret, they want you to describe what that number value that you've calculated actually means. So as far as the marginal cost function, I'm just going to take a derivative. So basically, What you're seeing here is, this 3/4 that I have up here on the exponent. I multiplied that to the 8 in front because that 8 is just a coefficient, and 3/4 times 8 is 6. I subtracted 1 from this to get a minus 1/4. The plus 300, the derivative of that becomes 0, so that's why you don't see anything following it. And they moved it around to say that 6 times x to the negative 1/4 power is the same thing as 6 over the 4th root of x. So that's the marginal cost function. For part B, they want you to evaluate what happens when x was 81. So we just plug 81 in. The 4th root of 81 is 3, so I end up with 6 over 3, which is 2. So the marginal cost value at x being 81 is 2, which means that if at that point, if I was to produce another one of these flashlights, such as what it is, then I would be basically paying $2 more to produce that additional flashlight. So at that point, that means basically at that moment, producing the flashlights are $2 at cost per flashlight. Now, as I produce more, that might change, and it could go up, it could go down, depending on the function itself. But essentially, at that point, since I'm making that many of them, it's going down overall as far as how much it costs per flashlight. So, and that's what this gets into. So it costs about $2 to make each one at that point. So you were given a pretty similar problem as the one we did as an example, except here now, here you're looking at the cost of purchasing software licenses, and the cost function is given by C of x equals 24 times x to the 2/3 power. You're asked to find the derivative of the cost function at x equals 64 and interpret the results. So, first I'm going to find the marginal cost function. Now they say MCX, I just use C prime x, same thing. It's just, that means it's a marginal cost. So again, very similar in nature. I multiply the 24 by the 2/3, which was the original exponent. I then subtract 1 from that 2/3. And so I end up with 24 times 2/3 times x to the negative 1/3 power. 24 times 2/3 is 16. So I have 16 times x to the negative 1/3 power, which is the same thing as me dividing by the cube root of x. So my marginal cost function is 16 divided by the cube root of x. So I want to figure out what happens with that when x equals 64. So I'm going to plug in 64, and I get that the marginal cost at the moment when I'm purchasing 64 of these licenses is $4. So essentially what that means is if I'm purchasing this many software licenses, that means that because of the number I'm buying, each software license is costing approximately $4 per license. Now, obviously, if I probably bought less, it would probably be more per license, and if I buy more, it might be even less per license. It really depends on the function that I have here, but this function kind of starts off pretty steep and then levels off considerably. So that would take looking at a graphing calculator or something, but essentially that's what's going on here. If I'm purchasing this many, then I'm getting about a cost of $4 per license at this point. Section 2.4 deals with two rules that we're going to be using a lot of as we do derivatives in these next couple of chapters. But right now you might think it's not as useful because of what functions they're giving us to do. Because in a lot of instances where they have us do the product and quotient rules, you could probably carry through to multiplication or division and simplify it, and then use just the power rules at that point to carry out the same thing a little bit more easily. When we start getting into other functions and use of what we're going to eventually call the chain rule, which is a rule that usually gives the students a lot of difficulty, then the product and quotient rules also have much more of a purpose. But initially they want you to kind of get the habit of using the product and quotient rules with simpler functions that you can actually do other ways, so that you can check your results and see if you can verify that they are in fact the same thing. So we're going to kind of go through both the product rule in this example and the quotient rule in the following example, which is basically the whole gist of what section 2.4 is going through. Knowing that this would be much more of a useful concept later when we have circumstances where simplifying is either very, very complicated to do if I carry through the multiplication, or in some cases I really can't do it at all because of the functions involved. So now the product rule simply says if I have a function made up of the product of two other functions, then what I need to do to evaluate its derivative, see, the sum and difference rules were pretty easy. Take the derivative of each thing and then add or subtract them together as the case may be. For the products, it doesn't work that way. It isn't me just saying f prime of x times g prime of x and calling it quits. The product rule says that if I take a circumstance like that, I'm going to do the derivative of the first function times the second function plus the first function times the derivative of the second function. So for instance, as an example, if I'm doing the derivative of this using the product rule, now again, this particular example, if I wanted to do this much more easily, I would just do x to the third times x to the fifth and get x to the eighth, and then use the power rule to say that's simply 8x to the seventh. That would be a heck of a lot easier. However, for the time being, knowing that that's what the answer should be, I should be able to verify that using the product rule as well on this function by not, by not carrying through the multiplication first by using the product rule. As I said, for the time being, they're going to have you practice it just to get used to the steps involved, even though there is going to be a lot of simpler ways of doing it. When we get to some other functions, once we've learned about a few other different properties of derivatives and other specific functions, there's going to be cases where we can't multiply the two things together very easily, like I could here. But if I follow the product rule, I'm going to do the derivative of the first term, which is going to be 3x squared times x to the fifth, plus the first term times the derivative of the second, so x cubed times 5x to the fourth. Now when I do that, I'm going to get 3x to the seventh plus 5x to the seventh, which ends up being 8x to the seventh. But as I said, I could have done that a heck of a lot more easily if I had simply carried through the multiplication to begin with and went from there. But as I said, I want you to get used to this notation with these easier functions so that when we get to circumstances later where we cannot carry through the multiplication to make it easier, you have this at your disposal. Certainly, if I asked you a question like this, I'd probably do it the easy way myself and just say, well, that's x to the eighth, and the derivative that's 8 times x to the seventh. So, but let's have you give it a try with the product rule and use the product rule on this one. Oftentimes when you're given a product rule problem, you're going to be asked not to simplify the expression. So that's what I'm going to ask you to do here. So in this example that you were asked to do, we're already approaching a situation here where, yes, I could carry through and multiply these two quantities together by using the distributive property in a process very similar to doing the process we call FOIL. But you would have a good number of multiplications to do, combining of like terms and so forth along the way. So, you'd have some complexities in carrying through the multiplication. Whereas here, if we kind of just use the product rule and don't simplify, it might make it ever so slightly a little easier to handle. And the reason why you're also being asked in a question like this, and you will see this from time to time, not to simplify, is there still might be tests or quizzes where, a calculator is allowed on some parts, but not others. Not the final, obviously, but, in some parts, you're asked to use a calculator and you can use it. In other parts, you're asked not to. If you have a calculator that would do the derivative of this for you, it's going to automatically simplify, combine like terms, so forth and so on. So it's not going to show you intermediate steps. And using the product rule and leaving it as it is, you're kind of showing some of those intermediate steps that the calculator is not going to show. So as a result of that, to do not simplify your solution kind of lets, the person grading your quiz or test, whatever the case may be, see if you actually do know the product rule. So I am going to use the product rule on this. So as I use the product rule on this, again, taking the function, leaving it as it is. As I said, I could have simplified it a bit and, just use the power rules, but I chose not to. I chose to use the product rule because it told me to. I'm going to do the derivative of the first, which is going to give me 4x to the third minus 12x times the second, which is just me rewriting x cubed minus 8x plus 2. And then I'm going to add the first statement times the derivative of the second. So I'm going to have that x to the fourth minus 6x squared plus 8 times the derivative of the second quantity, which is going to be 3x squared minus 8. And that's where I'm going to leave it, because anything after that, I'd have to carry through foiling, combine like terms if I want to simplify that any further. And that's basically the response that you're asked to give for this one. Again, as we go through the quotient rule, which is the second part of section 2.4, again, the circumstances, many of the circumstances you're going to be given, you could probably carry through the division and make your life a lot easier going that route than using the quotient rule. Both the product rule and the quotient rule are rules we try to avoid if we can, without causing too much difficulty in the attempt to do so. The functions you're being given early on, you could probably avoid use of the rules under normal circumstances. But because they want you to get used to using the rules, they're going to give you it now. But as we get further on, as I said in the previous example, as we move further on into the course, we're going to get some products that we're not going to be able to carry through. We're going to get some quotients and we're not going to necessarily be able to carry through either. And therefore, the quotient rule comes in handy. So the quotient rule, a little bit more complicated. Again, not like the addition or the sum and difference rules, where I just, like, if I have a quotient, I don't just do the derivative of the top over the derivative of the bottom and call it quits. Students sometimes make up their own product and quotient rules, and that's where they lead to some difficulty. The quotient rule states that if I want to do the derivative of a function made up of f of x over g of x, where f of x is the top and g of x is the bottom, we are going to do bottom times the derivative of the top minus the derivative of the bottom times the top, all over bottom squared. That's the general procedure for doing the derivative of a quotient. So for instance, as an example, I want to do a derivative of x to the ninth over x cubed using the quotient rule. Now again, in this particular example, under normal circumstances, if I was given this derivative to do, I would actually do x to the ninth divided by x cubed, get x to the sixth power, and then do that derivative and say that's 6x to the fifth. Heck of a lot easier. However, to get used to using this rule, we're going to use the quotient rule and try to arrive at the same thing, that same answer, 6x to the fifth, preferably. So I do the bottom, which is x to the third, times the derivative of the top, which will give me 9x to the eighth, minus the derivative of the bottom, which will give me 3x squared, times the top, which is x to the ninth, all over the bottom square, which is x cubed squared. When I simplify, I get 9x to the 11th minus 3x to the 11th all over x to the 6th. Of course, I end up with 6x to the 11th on top divided by x to the 6th, which if I carry through the division now, I get 6x to the 5th. As I said, heck of a lot easier if I carry through the division in the original and do the derivative of that using the power rule. But they want us to get used to using this. Now, the example I'm going to have you do next is more of a circumstance where, the division, carrying that through is a little bit more complicated, and the quotient rule is of better use to us in this example I'm going to ask you to do next. So give it a try. Now, this example here, this is more of a better use of the quotient rule, simply because of the fact that me carrying through this division is not an easy prospect. There's no common factors between all 6 terms I see here for me to cancel anything out. Doing this division would require a polynomial long division, which is not fun in and of itself. So, and even with that, we wouldn't necessarily know how to handle that yet. As far as once I got the division carried through, and what I end up with as a result, I wouldn't be able to handle that very well because I would still need to make use of what we call the chain rule, which is something we're going to learn about later, to do it. So this particular example, I really didn't need the parentheses on top and bottom. I just kind of took the product rule problem from example 4 and made it a quotient rule. So the parentheses kind of stuck around because of that. But if I use the quotient rule on this, and here would be more of a beneficial one to do it with, I'm going to take this function here, and I'm going to do the bottom times the derivative of the top. So the bottom is x to the third minus 8x plus 2. And the derivative of the top is going to give me 4x cubed minus 12x minus the derivative of the bottom times the top. So the derivative of the bottom is going to give me 3x squared minus 8. The top, of course, is x to the fourth minus 6x squared plus 8. All over the bottom squared would just be me rewriting x cubed minus 8x plus 2 all squared. So, and that's all I'm going to do because I'm not asked to simplify again. And that's as far as I would go. If I wanted to go any further, I'd have to actually FOIL these out, see if there's anything division I could do. But even with that, I wouldn't be able to get very far because this doesn't simplify much further beyond this. So, excuse me. So that's all there was for this example. Let's move on to example 6. This example here, I'm just going to kind of go through the marginal average cost. I'm not going to have any interactive nature to this one because it's kind of like just do what's being done here and a couple of examples I give you for this. But it's often useful not to calculate just the total cost, but also an average cost per unit. And this gets really shaky because, a marginal cost is kind of like an instantaneous cost per unit at a specific time, whereas the average cost, an average cost per unit, and doing a marginal average cost per unit, it's, very similar but not exactly the same. Because the whole idea behind it is that an average cost is the total cost divided by the number of units. So, so when we're doing a marginal average cost or a marginal average anything, we're trying to find a rate of change for an average, so it gets kind of like shaky about, like, at times, you have to be really careful about what you're being asked to do. This kind of gets into something we call average value, and we're going to see that in other points in time during this course as well. This is kind of a prelude to that as well, so that's why they're bringing it up a little bit at this point. So, But obviously, as you can see here, if we're creating a function that's made up of a cost function over x, we are basically kind of creating for ourselves a need to possibly make use of a quotient rule. That's not to say, though, if I have a situation where I could possibly carry through that division and simplify it beforehand and avoid using the quotient rule, I should certainly give myself the opportunity to do that. So the marginal average cost is simply the derivative of the average cost function. Again, the word marginal is kind of indicating derivative as it is. And there is a marginal average revenue and a marginal average profit, very similar circumstances. Not going to get too much into this. Your textbook kind of gives you a few examples as well. So, as a matter of fact, I think this might be one of the examples that your textbook does go over. In particular, it's going to kind of walk through it and talk about it a little bit more, just so that we're, everyone's on the same page about it. So, this is my example 6. I forget what example it is for them. I think it's example 8 out of your textbook. But printing on demand is a recent development in publishing that makes it feasible to print small quantities of books, even a single copy, thereby limiting overstock of storage costs. For example, POD publishing a typical 200-page book would cost $18 per copy, with fixed costs of $1,500. So you have a cost function of 18x plus 1,500. They want you to find the average cost function. B, find the marginal average cost function. And C, find the marginal average cost at x equals 100 and interpret your answer. So let's walk through each part of this solution. Now, the average cost function, not too hard to do. It's just going to be the cost function 18x plus 1,500 over x. That's it. So that's my average cost function. The marginal average cost function, well, what I could do with this, I could use the quotient rule if I want to. I would say that it might be overall easier if you were to use, and what they do as well is they're going to carry through the division first and make this, instead of 18x plus 1,500 over x, they're going to make it 18 plus 1,500 over x, which is the same thing as 18 plus 1,500 times x to the negative 1 power. This makes it a lot easier to do as far as the derivative goes when I want to find the marginal average cost function. Because I don't have to use the quotient rule. I don't have to do bottom derivative top minus the derivative of bottom times top over bottom squared. All I have to do here is just do the derivative of these two things. The derivative of 18 is nothing. The derivative of 1,500 x to the negative 1 is negative 1,500 x to the negative 2, which is what my marginal average cost function would be. And I could also rewrite that as a negative 1,500 over x squared. So that's pretty easy to do because of the fact that I carried through the division first. And I put it in the power form first. And if you have the option of doing that, I fully recommend doing that. It makes your life a lot easier. Again, the product and quotient rules are very useful in many circumstances. But if you can find a way, through legitimate algebra, mind you, that you can avoid them, by all means, avoid them. So that's my marginal average cost function. Now for part C, I want to find the marginal average cost when I have 100 of these books being presented. So I would get negative 1,500 over 100 squared, which is negative 0.15. What does that mean? When 100 books have been produced, the average cost per book is decreasing by about 15 cents per additional book. So basically what I'm getting here is, what that marginal average cost is giving me is basically how much the the rate of change is increasing or decreasing at this point. So that's what's going on here. The next book is going to cost 15 cents less to essentially produce. And as I produce more, if I produce more books or request more books, overall each one subsequently is going to be about 15 cents less. Until I move a little bit further in the function, then I might have to see, like, if that changes in any way, shape, form, or manner. But that's essentially, what's going on there. The average cost is decreasing 15 cents per book at that moment. So this reflects the fact that while total costs rise when you produce more, the average cost per unit decreases because of the economies of mass production. So this is getting into like loftier things that you will certainly study in other business courses outside of business calculus. So in section 2.5, you start dealing with the topic of doing higher order derivatives, which basically means that you're learning to do a second, a third, if necessary, a fourth derivative. And the way they kind of present it in your textbook makes it sound harder than it is. It really isn't all that difficult. Basically, if I'm doing a second derivative, I am doing a derivative of the derivative of a function. If I'm doing a third derivative, then I'm doing a derivative of the derivative of the derivative of a function. That's all it means. I mean, you're basically, and there's no like really necessarily in some cases a shortcut of doing it. If you want to do the third derivative of a function, you're going to have to take the first and second derivatives first, make sure they're correct, and then do the third derivative. That's all it is. These have their uses, and that's why a higher order derivatives do come in handy. Now again, they're showing you different notations for second order derivatives. You're seeing, here is like different ways a second derivative could be represented. All of these are fair game. The third derivative, fourth derivative, they're very similar. So I'm not going to get into those too much. It's just make sure you know what the notation looks like, especially when you look at d2 f of x dx2 or d2y dx2. Those exponents of 2 there are not indicating a squaring. They're indicating a second derivative. So you have to be aware that if you're seeing a derivative function, usually those little d's, if you're using a Leibniz's notation, then that indicates it's not an exponent in the manner of speaking that we're used to using it. It's actually just a designation of what order of the derivative you're actually doing. So for example here, finding a second derivative using the quotient rule. And here they are going to use the quotient rule, I believe. So if I take the derivative of this, I'm going to have, bottom times the derivative of the top. Now, the derivative of x squared plus 1 is going to be 2x minus the derivative of the bottom, which is 1, times the top, which is x squared plus 1, all over x squared. Now, when you're prior to this point, if you're, we had a couple of examples where it said don't simplify. And that was just to make sure that you were doing the product or quotient rule properly and that you know the procedure. If you're going to do a higher order derivative, you had better simplify, along the way. And in these cases, it's also best to simplify, even before you start taking derivatives if you can. This one here we could have. We didn't, but we could have. They wanted to use the quotient rule on this, so that's what they're showing. So here I am going to simplify before I go and do the second derivative, because then, if I was doing a quotient rule with this function, it would be, more or less a little bit more nasty than I would like it to be. So 2x squared minus x squared minus 1 is what the top becomes. I had the x squared minus 1 on top and x squared on the bottom. So now, when I do the second derivative, I'm going to do, now going back to the previous function, the bottom was x squared times the derivative of the top, Derivative of the top was x squared minus 1, so I'm just doing the derivative of the first derivative. That's all I'm doing, and that's what they indicate over here. Minus 2x times x squared minus 1 all over x to the fourth. And again, there's some simplification I could go on, and I end up with 2 over x to the third power through simplifying. Now they do make a note that, and I think in the textbook they do make a slight note that you could have possibly done this a little bit more easily if you had taken the original function, carried through the division of x. So you would have had x plus 1 over x, and then carried through that derivative. You would have to carry through the resulting addition to get the same answer here, and common denominators and all that stuff. But it's possible to get it done. I mean, so keep that in mind, again, that, if you have the alternative of simplifying beforehand, take advantage of it because it makes your life a lot easier if you're able to avoid the product or quotient rules. And they're kind of showing this right here. If I take the original function and do this and make it x plus x to the negative 1 power, the first derivative would be 1 minus x to the negative 2, and then the derivative of that would give me negative 2 times negative 1 is 2, x to the negative 3 power, which is the same answer we got before. So again, the moral of the story, as I mentioned before, simplify before differentiating if you can. So, they start you with some problems that say, okay, don't do that. But, in the long run, that's exactly what you should do to make sure that you're making it the easiest way possible and less likely to make mistakes along the way. So for the function you were asked to do, which, is given to you as a product of two quantities, I'm going to show two ways that this could be done. Again, one being the easier way, one being the hard way. I'm going to do the hard way first. And the hard way, I think, in this circumstance, I mean, you have two-term things. So foiling would be pretty easy to do for this, and then you could evaluate that. But here, I'm going to leave them as they are and make use of the product rule. So when I do the first derivative, I'm going to do the derivative of the first times the second, so I get 2x times x squared plus 5. And then I'm going to do the derivative of the second times the first. It gives me 2x times x squared minus 1. Now, when I do the second derivative, I have now two products being added together. So I have to use the product rule a couple times when I do the second derivative. So this one here gets split into these two. So I'm going to have, basically the first times the derivative of the second. So the derivative of x squared plus 5 is 2x, plus the derivative of the first times the second, which gives me 2 times x squared plus 5. And then same thing with this. I split this into these two because I'm going to have, again, first times derivative second, which gives me 2x times 2x. And then I'm going to have the derivative of the first times the second, which gives me 2 times x squared minus 1. Now, at this point, I'm going to simplify. So 2x times 2x is 4x squared. 2 times x squared plus 5 is 2x squared plus 10. Another 2x times 2x is 4x squared. And 2 times x squared minus 1 gives me 2x squared minus 2. I have several like terms I can combine here, and when I do so, I end up with 12x squared plus 8. That's as simple as I can get it. Now, as I said, I mean, there was a lot of keeping track of, product rules because I used the product rule in actuality 3 times. One to do the first derivative, and then I had to use it twice in the process of making the second derivative. Anywhere along the way, I could have probably made this easier for myself if I had simplified by carrying through the multiplication along the way. As I said, if you get functions where that's too much of a task, then that's when the product rule becomes handy. And you're going to find that there are some instances where multiplying through the two quantities you're given is impossible because of the functions that are involved. Eventually, we're going to do like, x plus 1 times the log of x plus 2. I can't multiply those through because of the logarithm involved. So that would be an instance where I have no choice but to use the product rule. In some cases, I could choose to use the product rule or not, and there's other cases where, like, I should probably, find a way of simplifying first and then using the rules that I have at my disposal at that point. So the easy way for this one would be for me to actually carry through the foiling first. If I do x squared minus 1 times x squared plus 5, I would get x to the fourth plus 5x squared minus x squared minus 5. And when I combine my like terms together, I would get x to the fourth plus 4x squared minus 5. So the first derivative, pretty easy. I just have to use the sum and difference rules along with the power rules, and I'd get 4x cubed plus 8x. And then when I do the second derivative, again, power rules, constant multiple rules, and a sum rule here, I would end up with 12x squared plus 8, which is the exact same answer I got in the previous answer. So it doesn't matter which way you do it. I mean, obviously this one I felt was a little easier to get to the answer. It was less steps overall, and less steps overall means that you have less likelihood of making mistakes that you don't want to make. So that's all I have for this one. Only one more example, and we're done with this 3 sections. The area where derivatives and higher order derivatives are made use of is when you start making, discussions about velocity and acceleration, which gets used a heck of a lot more in scientific calculus. I mean, you're going to have some instances where you talk about it here, but there's other rates of change, and equivalent to acceleration when you have a rate of change of a rate of change. That happens as well, and that gives you some descriptions about what's possibly going on with the various functions. So velocity and acceleration is one of the areas that these things come into play. So basically, if you have a function s of t, where s stands for your distance in miles and t stands for the number of hours you drive, s prime of t would give the instantaneous rate of change, or basically your speed in miles per hour at a specific time. So that's what the derivative would use. Of course, the second derivative would be your acceleration. So they're kind of giving you this visual here. This is from your textbook. So miles per hour means speed or velocity. So derivative of the distance function is just the velocity function. And that's what we're kind of getting into here, and I've kind of already mentioned it. So they use a lot of words to basically say something that's pretty straightforward. If you have a distance function, the derivative is velocity. If I have a velocity function, the derivative is going to be your acceleration. Now, the acceleration is, the velocity means I might be going at a certain speed. The acceleration means, okay, am I increasing to that speed or decreasing? Am I speeding up or am I slowing down? And that's what an acceleration is. And there's equivalences in other instances as well. So basically, if I'm giving a distance function, the first derivative is velocity, the second derivative is acceleration. So for this example here, a delivery truck is driving along a straight road, and after t hours, its distance in miles east of a starting point is 24t squared minus 4t cubed. For t's being between 0 and 6, so for the first 6 hours, it's following that function. So in part 8, I want you to find the velocity of the truck after 2 hours, find the velocity of the truck after 5 hours, and then find the acceleration of the truck after 1 hour. So first I'm going to figure out what the velocity function is, and that's just by me taking a derivative of the distance function. So the velocity function is 48t minus 12t squared. And if I plug 2 into here, I end up with 48. So I have 48 miles per hour. So the velocity after 2 hours of the truck is 48 miles per hour. Now, one of the things that they are mentioning is that it's heading east. If I have this function, I mean, and since there is a possibility to it, if I would have a negative of this, that means it would just simply be heading west. And that's kind of, I think that might go on in this one here, I'm not sure. Yes. So here we have negative 60 miles per hour. That's its velocity. So basically what's going on with this function and what this function is describing, you know, in that 6-hour time, it went east, and then it's coming back and heading back west again. And that's what the negative stands for. I can't have a negative velocity, I mean, a negative speed. I can't go negative 60 miles per hour. Negative 60 miles per hour simply refers to the fact that, you know, since we're talking about that the velocity was measured and the distance was measured eastward, this indicates that this truck at that point in time is heading westward. The acceleration would be the second derivative, or the derivative of the velocity function. So the acceleration function would be 48 minus 24t. I plug 1 in, I get 24, which means at 1 hour, its speed is increasing 24 miles per hour squared. So it's speeding up. So its velocity is getting greater at that point. So the velocity, you know, we know it's probably eastward, and it's getting greater. The second derivative has other meanings besides acceleration. In general, second derivatives measure how the rate of change is itself changing. So the first derivative measures the rate of growth, then the second derivative tells us whether the growth is speeding up or slowing down. And so in the case I'm going to give you to look at here, we're dealing with, again, a cost function, or the value of a stock. And I want you to be able to use first and second derivatives to interpret what's going on at a specific time. So that's what you're going to be asked to do in the following problem. So for this problem that you were given, you were told that the value of the share of stock in dollars in Sorrentino Incorporated. Hey, I'm the one who's writing the problems and doing all this work. I get to put my name in it. It's given by this function here. And you can see it's written currently as a product of 3 quantities plus 300. And the function, it represents, you know, basically the cost of the stock in dollars, where T represents the number of years past 2000. You're asked to find which of the following describes how the value of the stock is changing in 2018. So it's basically asking you, is the value of the stock increasing in value in the rate that it is increasing is intensifying, which means it's getting, you know, it's going up, you know, so not is it increasing, but year to year it's increasing by a bigger amount. Is the value of the stock increasing, but the rate that it is increasing is declining, which means, okay, I do expect it to go up in value next year, but not quite as much as it did this previous year. Is the value of the stock decreasing in value, but the rate that it is decreasing is declining? So basically, you know, in this case, it would be like me expecting the stock to go down in value. You know, it's gone down in value this past year, but next year it's not going to go down as much in value. So like this year, it may have went down by $10. Next year, I expect to maybe go down by $5 instead. That's what C is talking about. And D, the value of the stock is decreasing in value, and the rate it is decreasing is intensifying. So that means, like, you know, not only is it decreasing in value, I expect that next year it's going to decrease even more so than it decreased this previous year. That's probably a sign that the stock should probably be sold off as quickly as possible, or, you know, before you lose your shirt. So how am I going to determine this, though, with this function here, which only tells me what the value of the stock is going to be? Well, let's have a look. So I'm going to first look at the function, and I'm going to figure out what the first and second derivatives are, because they're going to lead to me being able to answer these questions. So first of all, I take S of t and I do simplify it. I don't show all the foiling and distributive property and combining like terms, but essentially when I simplify that function, I do get t to the third power minus 35t squared plus 336t minus 420. With that being the case, it makes finding the first and second derivatives a heck of a lot easier. I don't have to worry about using a product property, especially when I have three quantities being multiplied together. That makes it even worse. So before I get into having to worry about doing something like that and keeping track of all that, I'm simply going to just, simplify it first. When I do the first derivative, I end up with 3t squared minus 70t plus 336. When I do the second derivative, which is just the derivative of the first derivative, I end up with 6t minus 70. So now I have a function for the first and second derivatives. I'm going to evaluate what happens at 18, which, t being 18 would represent the year 2018, which is what they asked us about. So when I plug in 18 to the derivative function, which would basically give me the rate of change for the stock. I mean, is it increasing, decreasing? Basically, I'm getting $48 per year, which tells me that the stock is increasing by $48 per year at that point. The second derivative at 18 ends up being 38, which basically the $38 per year squared, which basically means that not only is the amount of the stock increasing, the amount it's going to increase the following year, I would expect it to be even more so than it was the previous. So, so basically the next year I would kind of expect it to more or less change by about $86 per year more in 2019. That's more or less the expectation. So it's gaining in value and also increasing how fast it's gaining in value as time goes by at this point. So based off of that, not only is it expected that the stock will grow beyond 2018, but grow even more from the time period following 2018. So that goes along with, the description given in A. The value of the stock is increasing in value, and the rate that it is increasing is intensifying. And that's the end of this example. If you have any questions with anything we covered in Chapter 2, please feel free to bring them up in class or see me during office hours.